Hello community, so great that you are back. Today we have an absolute fascinating topic. We have a possibility to copy the complete brain of an agent, send it over to another agent without generating any words, any human language. And it is up to 7 times faster. Let's have a look at this. Welcome to my channel Discover AI, and we have some beautiful new papers today. Let me show you. Can you imagine this? You have 2 agents, and normally you have here the transformer architecture of agent 1, and then the sorts are generated and transformed into token. The token is identified with the vocabulary to a word, and you have an autoregressive word-by-word generation, and this is then transformed with human words to agent B, and then agent B is converting this, and you might say, why? Why we are doing this? Why we cannot have here an ultra-fast communication here? Without any human language. The agent doesn't need a human language, just we are. As humans, we want to see a human output. But why we have an intra communication between our agents in human language? That's nonsense. So therefore, Princeton, Stanford, and somebody else, University of Illinois, decided, hey, let's have a look at this. And they had the idea, what about we take all the key value data from all the different transformer layers here, and we just send it over here to the agent B. And of course, we have to take care about the last layer, the hidden state H here, our activations. That is not a result of all the thinking of agent A. How can we do this transfer? Let's have a look. Key value data, you know that the model model saves here the key and the value vectors for every token it has ever seen in our conversation. So we do have the data. We just have to send it over. That's all the complexity that we have. But of course, for a chain of thought, the thing will get so much more beautiful. But let's start easy. So what we have? The old-fashioned way, an autoregressive loop, an internal thinking of a transformer. Yeah, I know. We have a token passes through the transformer to all the layers, flows up from the layer 1 to the layer 2 to the layer 32. And we have here a high-dimensional vector H, and in this rich high-dimensional contains here a fuzzy probabilistic belief, like, hey, it's 60% that it will be the fact A, and 40% likely to be the answer is B. And then we have a projection, and the dense vector is multiplied by the language head matrix to get the logits. Remember, depending on the vocabulary size, 50k to 150k. And then everything is collapsing to an integer with some softmax function and the sampling. So the model now applies sampling the softmax function and picks now from the probability distribution one winner. And this is the token ID 4598. And if you look at the vocabulary, we identify this token ID with the word therefore. This is all there is. We collapse the complete next token prediction probability distribution density process into the word therefore. Beautiful. This is the way a normal transformer thinks. But you know what? By using now the hidden state of the last layer of the transformer itself, not converting it into the stupid human language, we can preserve the super expressiveness of this abstract, if you want, AI sort of a transformer layer before it gets limited here that we have to reconvert it to a human language. We don't do it. And our new archive preprint here, especially Theorem 3.1, gives a mathematical proof that the hidden layer can carry much more information, and this information cannot be efficiently expressed at all in our old text tokens, in our human words. So if we stay to an internal transformer hidden state activation level, and we have this as a communication level between multi-agent systems, why the hell do we transform this into the human language? So here we have the surprise of my weekend. Princeton University, Illinois, and Stanford University. Beautiful paper, latent collaboration and multi-agent system. You are not gonna believe what they prove. They have Theorem 3.1 about the expressiveness of latent sorts under the linear representation hypothesis that is detailed here in the assumption here B1. If the sequence of all latent sorts with a length m can be expressed losslessly through a corresponding text-based reasoning, then the length of text in tokens need to be at least at a particular complexity. And then we have the remark 2.3 that suggests that a latent sort generation can be of a particular order, much more efficient than a text-based reasoning. And you say, no, I don't believe this. And I looked at this and said, I mean, I have a feeling, but can you prove this? And yeah, of course, here's the proof of theorem 3.1. You find it here, and they go here and they prove it mathematically to you that this is possible. So we do have, if you want, no, it's not a logical compression. Before we reduce it to the human language, we stay in the internal mathematical latent thinking space of a transformer. And then we come to innovation number 1. And I think it's beautiful. So Theorem B2, or restate of Theorem 3.3, tells us now, in both latent and text-based reasoning of our AI system, the output of an agent when receiving a latent working memory from a preceding agent, so agent 1 if you are agent 2, are equivalent to those obtained when directly inputting the preceding agent's outputs. So we can do, if you want, brain.copy between agents. This is not a communication process. I just say brain.copy key value cache from one agent to the other agent, and I don't need to build sentences. Hey, I'm agent 1. I like to communicate now to agent 2, and my findings were, and ABC. Forget about it. We communicate in tensor structures, inter-agent. So instead of sending here the output, the result of the thinking process in words, agent A sends now an internal memory state, the process if you want, to agent B. Isn't this nice? Now, you might say, okay, let's have a look at in the embedding. Let's take some particular dimension here, embedding space 1 and embedding space 2. And they did it, and they had simply a look at the embeddings and said, hey, if we have a complex mathematical space, can we make sure that our new embeddings that are generated now by this latent sort generation multi-agent system configuration is more or less at least covering the space that we had with the old-fashioned textual human language multi-agent system communication pipeline? And you see it here for Xiyuan 3, the 4 billion model, the 8 billion model, and the 14 billion free trainable parameter model. Look, the orange dots are the textual and the blue dots are the new latent system. And you see, yeah, the blue dots even have here a much wider space, so they have maybe even more expressiveness here and complexity that the human language cannot carry as easily. Look, orange here, especially at the 14B, Xiyuan 3, orange is rather clustered, and the blue one, the new methodology, uses more space, which is interesting. We have to look here at the complexity of this, if you want, manifold hyperplane structure, but more about this later. Let me give you an example. Examples are always great. So they have a study here, and you have here the complete here in the annex. You can read this step by step. So they have a question. Okay. And they go at first with the old textual human word communication between multi-agent system. And you have a planner agent, a critique agent, a refiner agent, and then a solver agent. And you see here, given here a particular input query, the planner agent, this is the output of the analysis. And this is the input to the critique agent. And the critique agent's job is to critique this, has an input from the planner, critiques this, and the output of the critique agent is now the input for the refiner agent, and you got it. And they give you an example. After all of this, we get the wrong answer. So text multi-agent systems simply fail. Great. And now they say, hey, I give you now the prompt template for the latent multi-agent system communication without any human words. So here we have it. Now, for a particular numeric task, you have to specify, of course, this for your knowledge domain and for your task complexity. So you cannot use just one prompt for everything. You have to be very specific. But you say, hey, system prompt for all agents. You are Xiyuan, created by Alibaba Cloud. You are a helpful assistant. You know, I love it if Stanford and Princeton are not working with American AI models like GPTs or whatever. They are going and using here Xiyuan Chinese models. You know why? Open source. I don't tell you anything else. So we have now the prompt for the planner agent. You say, hey, you are a planner agent, given the input. Yeah, and you can see this here, prompt for the critique agent, for the refiner agent, and the prompt for the judge agent. And you know what? If you do this, you see at first it is much shorter because you just copy the brain from one agent to the other. You don't have to write down any explanation. You just have a tensor mapping, and the latent multi-agent system succeeds with a complex chain of sort process here, where you just copy here the temporary brain of one agent to the next agent and to the next agent, and you get the idea. I was talking to my Nano Banana Pro, and you see this is here one of the images I like. If you have two agents, agent A on the left side, agent B on the right side, and you have agent A conditioned for a particular topic, let's say mathematics, and agent B is conditioned more for theoretical physics, to go a little bit higher in the complexity, or astrophysics. You can just copy a temporal slide here, or the complete brain of agent A, send it over to agent B as the input, so you wake up agent B, and then you can use here the specialization of agent B, that is theoretical physics or astrophysics, but having the complete process understanding of agent A, not only the result. The result might be, hey, this parameter is 1.4. Yeah, but what does it tell you? Nothing. It just gives you a result. But if you really do research, you want to understand the process, the way the agent A came to be to this result. What were the algorithms that it was used? How was the complexity of the thinking process? What were the data? Did it use a computer simulation? Did it just had an algorithm? Or did it really calculate it here with extreme high precision? You want to have the complete memory, all the working files, everything. And everything is just copied here into the brain of agent B. And then agent B goes on with its specialization. And this was just the input. You can transfer mathematical and theoretical complexities that are much deeper and helps much better in the reasoning process, because you do not just transfer the answer. Yeah, the parameter A is 12.8. I'm loving it. So let's summarize this. It's so easy. That's it. Latent sort generation. So what we had to do, Princeton, Stanford, and Illinois had to do. Simple steps. I think this is the second big innovation of this paper, and seldom that you see two main innovations in one paper. I think what's so nice here is the silent thinking in one agent, in the intra-agent communication system. Because you can have a high-density reasoning vectors that are far more expressive than any textual description, and they have the mathematical proof in the paper. Read the paper, send a thank you note to the authors. I'm loving this paper. Okay, this latent sort generation enables an LLM to reason silently. So it decouples the reasoning process inside of the AI agent from the constraint of using here a human vocabulary. So instead of forcing the model to select a specific word or token at every step, next token prediction, the system captures here the model raw brain activity, all the hidden state, all the activations here from the hidden layer, and loops it back into its own senses, back into the input layer to simulate here the next sort. So first, a token bypass. This is the main deviation, in standard LLM would be projected to the logic and passed to the softmax function to select here a token ID with the word therefore. Latent multi-agent system say, forget about it, I'm not gonna do this. It does not compute the probability, it does not sample here discrete token, it just performs a surgical bypass. Great. But then, and I will explain this in detail in a minute, we have an input-output alignment. And this is the prism that you saw here on the top level here above both agents. Because as it turns out, if you look at the mathematical space that we're operating with, those spaces are not really coherent and compatible at first glance. So the raw output vectors here, the age, the hidden activations, are statistically distinct, if you want, in their geometric shape from the input embeddings. So if you would fed this directly back into input level 0, they would trigger an out-of-distribution activation, degrading here the performance of the reasoning process, and everything would collapse. So the authors thought, hey, no problem, I have a particular geometric space A, and I have a particular geometric space B. So what I do in mathematics, I create a projection matrix that maps here the output vector back to the valid input space configuration, and it is just a mathematical operation. Times it can be that easy. So I'm going to show you how to build this, and then they said, okay, now if you have an aligned vector, that is here the next vector, this aligned vector is now treated exactly as if it were a standard token embeddings here in the input, in the first layer of the transformer. So we just proceed as normal. Nothing special happened. So the model runs now the forward pass again. Because of the key value cache, the model only computes it a new step. This produces here a new hidden state, and we just go on with everything. Isn't this beautiful? So what we have now in single agent, we have a sort stream generated. Because this cycle now repeats for a predefined number of latent steps that you can say 40 or 80 or whatever you have the budget for. And this now results in a sequence of latent sorts in the single brain of agent A. Even now the reasoning process in agent A is not anymore coupled to human words communicating an autoregressive token prediction process. Forget about token. Forget about this vocabulary structure in the reasoning loop itself. Yeah, at the output, okay. But in this thinking process, why should we go with a predict the next token? You can stay in the complex mathematical space and have your mathematical operations over there. So you will get a sequence of latent sorts, ht plus 1, ht plus 2, and yeah, m is defined at 40. So you see, beautiful. Whenever you run through here the complete layer here of your transformers, you get a new latent sort representation. You see, this is it. This is the end of latent sort generation. I'm loving it. Now, Stanford tells us, Princeton tells us here, we have 3 main insights. And I want to show you this because it's really beautiful. Reasoning expressiveness of this system. Those hidden representations in a single brain of a transformer of an agent naturally encode the model's continuous sorts, allowing each latent step to convey far richer information and a high information density than we have with discrete tokens and convert it back to words. Second, communication fidelity. The latent working memory preserves the input representation and the latent sort itself of each model, enabling, and now it comes, a lossless cross-agent information transfer. You just copy really the neural activity of each neuron of the brain. Third, the collaboration complexity itself. Because the latent multi-agent system configuration here achieves a higher collaborative expressiveness than the text multi-agent system, while achieving a significant lower inference complexity compute. You know what? There's a fourth fact that it's just an add-on beauty and it is completely training free, enabling all the agents to sync and interact purely through their internal latent representation. It is already there. We just have to rewire their brains internally, and this is all there is. Okay, you find all the code, you find all the data, you find all the Python files here, all the models that you need here, beautifully. GitHub, Genverse, Latent Multi-Agent System here by Princeton University. Have a look at this, it is just great. Let me give you the results. The results are just amazing from the efficiency point of view. For the inference speed up, since we don't have to convert here every time back to a human word and then feed this human word back in and convert it back to a tensor, and then you get the idea, it is on average up to 4 to 5 times faster at the inference. For certain tests, even 7 times faster. This is beautiful. And look at the system-wise token usage. You know that you pay per token. You can reduce the tokens now up to 83%, 84%. Now I think if this will be implemented as an operational mode of the next generation of AI systems, the global corporation will change how you gonna pay. Maybe they will deviate from the pay per token usage to something else. Because this would mean that with just the same performance of the system, and even maybe a better performance, the system is now 83% cheaper for the same output. Can you imagine this? Because we do not just convert back to human and use human language here for the inter- and intrapersonal, agent communication. Now, what is a little bit disappointing for me personally, yes, of course, it is always better, but it is not a significant jump here in the performance, in the reasoning performance. You see here for all the different benchmarks here, beautiful in the circle. In green, you see the single model performance. Okay, this is here the worst if you want. Then in orange, you have here the textual multi-agent system communication, the traditional one where everything is converted back to words. And then the light blue one here is the new latent multi-agent system, and you see it outperforms here all the other systems. But it is not. Yes, sometimes it is real close, just 1 or 2 percentage points. Sometimes you see a more significant jump. So a clear indication, this is just the beginning. This is just the first implementation. And even I have 2 ideas how we can further optimize this methodology. Anyone said, wait a minute, you can't stop the video here because you did not explain here this strange little star, this prism on top here above both agents. And I mean, you're talking about this. Yes, of course. As I told you, if we have here our agent A and we run through here all the layers of the transformers and we have the hidden activation if you want, and we have, as I already told you, to feed it back into the input layer back again, we have to find here a mathematical optimization. So let's do this now. Now, you know, classically, I already mentioned it, softmax function is a lossy compression algorithm. No? It's a rich continuous probability distribution as calculated here within the layers of the transformers. And it tells us, hey, the solution is to 60% it is an apple, to 39% it is maybe a banana, and to 1% it could be a car. But then, after softmax, it collapses into a single integer ID. It is an apple. And we lose the information that there is still a 39% chance it's a banana. We lose the context complexity entirely. The vector is destroyed and replaced now by dictionary lookup results. So we crush the complexity down to a single token, maybe to a single word, like apple, and this is the result here from our autoregressive LLMs. Now, in the latent multi-agent system case, you remember, we keep now the complete high-dimensional rich vector. But we cannot just plug this output wire back into the input slot because, let's say, the voltage is not there. Né? So we must modify this. And this means simply the geometry of those both mathematical spaces have to be adapted, straightened up. How we do this? What is this prism here? It is, of course, a subspace alignment via a linear projection algorithm. I told you, it's just mathematics. So let's have a closer look. This is here this prism now. Né? So we have here the output from all the different transformer layers here. We have here the raw hidden state, beautiful, so it goes in. And if I want to use here the output now for a continuous reasoning process, I have to transform this so that the geometry of this data stream becomes now the perfect geometry of a particular layer. I want to feed this information back into the transformer, or maybe to the input layer, to the very lowest layer of the transformer. Né? So I have to simply perform a mathematical operation. I have to have an aligned input to the dimensionality that this layer is expecting from the signal, because the complexity of the output signal, it is not expecting at all. Output space, input space vectors are normalized, compact, spherical. They're optimized to trigger the first layer of the neural net. So you have to take care about this. So what we want, in the simplest mathematical idea I can express this, we just want to find a matrix WA, no? Such as the matrix W out times the matrix WA equal the input dimensionality of our layer complexity. So what we need is just here this matrix WA. So if you look at this, you say, hey, that's easy. So we just compute the pseudo inverse of the output head and multiply it with the input embedding WN. Of course, this is it. So this is the formula how you code WA, what you're looking for. This conversion matrix that the output signal is now in the right geometric precision and shape to be inserted or feed back into the input loop of the first transformer layer. This is it. You can calculate this. But there's about the stability of this system an interesting aspect. No? This prism, this WA, replaces now the dictionary lookup for a human word. No? And in the old method, this text lookup stabilized here the sort process of our old transformer by snapping it to a valid word. We reduced the probability distribution. It could be a car or an orange or a banana, and it stabilized it to a pure singular decision. It is an apple. If we do not have this and we would run 40, 50 times, there could be some problems with the stability of the system in total. So this new method, this latent multi-agent system, we use now this WA matrix to stabilize here the sort process by simply aligning now the vectors in the perfect way. So the system is now stabilized by itself, by mathematics. And then if we have this internal loop of agent A, we can loop this continuously. No? The agent can now think 40 or 80 steps in a fraction of a second, building up here a real complex reasoning trajectory before it even talks to the next agent. And now it's not talking, but it's just copying its brain activity and sending over the brain activity of the final temporal state to the next agent. The next agent, who is the astrophysics, who just needed the mathematics as an input, can now continue to argue with its domain-specific reasoning. But of course, at the end of this video, I have to tell you why I'm not rushing over and using it already, because think about it. I think there's multiple risks, but the main risk is error propagation. And you know, every agent, every LLM still hallucinates in one form or another. So in the text-based system, the agent A makes a mistake, agent B might catch it by the input, because it reads here the text critically. You can even have a scanning LLM in between the communication of agent A to agent B, because the text is now in the classical old form in human words. And the LLM analyzer can tell you, hey, that sentence doesn't make sense. This is nonsense, no? Now, if you do not have anything that, for example, a human can read in the intercommunication between the agents, no? The transfer, you say BRAIN.COPY, and you send it off and you get done, is a little bit more challenging to implement here security features, no? Or correction features. How you want to make sure that there is not at all a hallucination happening here, because if agent A makes a mistake or hallucinates somewhere and sends over this hallucination as an input to the brain of agent B, this hallucination is transferred in its complete complexity and can have massive negative impact on the reasoning process of agent B. So the reason why I'm trying to test it out and maybe find some safety features to be implemented is if you have 5 agents and you just let them think internally, and every of those 5 agents can hallucinate. And if it's only a hallucination rate below 10%, below 5%, below 1%, it would cascade through all the argumentation and the logical reasoning here. Everybody copies their brain, and there are hallucinations in this brain, and they just exponential go up. I love the idea of this AI brain transplant functionality between AI agent. It is great, but maybe I wait here for the next publication by this team. Now that we have established this methodology, we just need to work a little bit more to make sure that we have really a validated reasoning process. At the end of this video, I just recommend read the paper. It is really amazing. You have so many more numerical test data in the detailed description. But anyway, I love both innovations that we can implement really already in the next generation of AI. So maybe you liked this video, maybe you found some new information. Anyway, I hope you enjoyed it. Maybe you subscribe to my channel, maybe you become even a member. But anyway, it would be great to see you in my next video.